years to have insight on why a particular problem he was talking about could not, well, it turned out later, proven to be impossible to solve. But the idea that you could prove that something was impossible in the algorithmic sense was just unknown to him. Right. So what was this problem that Hilbert was talking about? Okay, so Hilbert's famous for a lot of things. In the turn of the century, like more than a century ago, 1900, in Paris, a famous meeting of the International Congress of Mathematicians, the ICM. Now, this meeting is famous every 4 years, and at the meeting is announced the winner, or usually winners, of the Fields Medal, which until recently was sort of like the Nobel Prize for mathematicians. Now, Nobel himself, the guy who discovered dynamite, he made a fortune and set up the Nobel Prizes. Now, he did not include mathematics as one of the categories for the prizes, and there's a bit of a mythical story around that his wife had an affair with a mathematician, and therefore Nobel excluded mathematicians from his prizes. But it's a myth for the simple and obvious damaging little fact that Nobel was a bachelor. He never married. Okay, so it looks as though the real reason why he did not include mathematics in his prizes was simply he just wasn't interested in mathematics. It just wasn't, just not on his radar, so to speak. So, since I think the 30s or so, the most prestigious prize in math has been the Fields Medal. So some guy, Canadian, not sure, a guy called Fields set up a prize, and it's won every 4 years, so it's harder to get than a Nobel Prize, and it's ageist, unfortunately, but the mentality of the time. You have to be under 40 to get the prize. So if you're a mid-career switcher and you come into mathematics later in life, you're prejudiced against. Okay, now since 2003, I think, finally a lot of complaints from a lot of mathematicians saying there should be a Nobel Prize equivalent for mathematics, awarded every year, and $1 million for the prize. Just the same as for the other Nobel Prizes. And in 2003 it was set up, and it's called, now it's not generally known amongst the general public, and to you maybe this is the first time you've heard this, but this equivalent to the Nobel Prize for mathematics is now called the Abel, A-B-E-L, and Abel was a famous Norwegian, I think, mathematician, one of the pioneers of group theory, finite group theory. And so now every year since 2003 the Abel Prize is given, and it's equivalent to the Nobel Prize. It's prize money is, the value of the prize is much the same. So anyway, so for years, for decades, at the ICM, the Fields Medals are announced, and it's only every 4 years, so it's a big meeting, and mathematicians from all over the world come and hear the latest ideas and hear the best brains in the world in mathematics, and the best brains in the world, because they tend to be the smartest guys, present the latest thinking and ideas. Now, at the time, Hilbert was pretty well the top guy on the planet for math, so he gave a keynote speech, sort of invited speaker, and it was 1900, right? So an auspicious time, and so he decided, instead of talking about the recent successes of the past, presenting state of the art, he was a rather zany, creative sort of guy, so he did the opposite. he talked about what's not known. And so he presented a list of 23, I think, yeah, 23 unsolved problems that he felt were important for the future, near and relatively near future of mathematics. Now, he was Hilbert, right? He had this broad overview. He was a genius. He could look over the broad sweep of mathematics and, with his nose, mathematical nose, sense which problems were significant for the future development of mathematics. So he used his enormous experience and his brilliance to write out a list of problems that he thought mathematics should solve, hopefully solve in the 20th century, the then new century. And those problems have become famous. They're just simply called the Hilbert problems. And if you solved one of them, well, you became famous for solving one of the Hilbert problems. Now, the most famous unsolved problem on the Hilbert list is the Riemann hypothesis. Now, I won't go into details, but if you can solve it, you'll get $1 million. If you can prove the Riemann hypothesis. Now, I'll say a little bit, but not too much. It's connected with the mathematical theory of prime numbers, so number theory. And it's a particular hypothesis that Riemann, one of the greatest mathematical genii of the 19th century, he lived in around mid-1800s or so, he came out with a hypothesis concerning the position of prime numbers as you count up, one by one. So he had a formula that would allow you to predict whether a particular integer was a prime or not. And out of that work came a particular hypothesis, rather somewhat advanced. And that problem has plagued mathematicians ever since. And all the top brains they haven't tried doing it and have not succeeded so far. Anyway, so that was the Riemann, proving the Riemann hypothesis. I think it was problem number 8 of these 23. Now, nearly all of them over the past century have been solved. So if you solve one of them, you become a member of the prestigious Hilbert Problem Club. Okay. So anyway, now one of them, the 10th of these 23 problems, was an algorithm type problem, and well, I'll go in, I'll actually give you the problem, statement of the problem, but it'll be in the next session. But it was the 10th of Hilbert's 23 famous problems, and interestingly, Hilbert just assumed that an algorithm was out there. It did not occur to him, because it was 1900 then, that it might be possible that such an algorithm is impossible. Right? That it just didn't occur to him. And it took quite a few decades later, that once the notion of what an algorithm was, once that definition had been made much more rigorous, that people were able to prove that such an algorithm, to solve this 10th problem, was actually impossible. And in fact, one of the courses, grade level courses, M2, second year master's level, in computability theory, will be taken from this book, Computability and Unsolvability, right? Now, interestingly, there are two appendices at the end of this book, and Appendix 2 is entitled Hilbert's 10th problem is unsolvable. Right? That's 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 27, 29, 31, if I'd look, 33, 35, 37. 37 pages on that problem, proving that that particular problem, which is an algorithm type problem, is unsolvable. So it has a famous history, and we'll talk about what the actual problem is, and use it as a kind of lead-in to the idea of unsolvability, but that's more a topic for the next session. So I'll talk about the actual problem, 10th problem, next session.